Comes on everyone. Let's start off. Sure. Let's start off. Everyone comes on. The last thing we were doing was this. We are visualizing stuff and we are trying to solve. So let's see one more like this. So this was the last thing that we did. So whenever this block B goes forward, if you see the motion is not happening only due to the tensions, but it is also happening due to the normal reaction between them. So if you try to use the power method, you won't get a complete answer. See, you will get the acceleration in the vertical direction, but you'll never get the horizontal component. So we did something of this sort. We pushed the block by x forward, and then we saw what is happening to the motion, right? We observe A is going front by x, and it is also coming down by 2x. Hope everyone revised this in the last class. Right. Let's see one more problem like this. Others, do keep your cams on. Yeah, we got a block like this. This is B, this is A, and this is theta. So if this block A is going with U, find BB. Whoever is having issues with the cameras, please sort it out. Next class, I won't allow you guys. How do we do this? Hope the picture is clear. This is a little more complex than the previous one, but idea is still the same. So move the big one by small x and see how many strings become loose, and then try to figure it out. Try, take a minute. So if this thing goes x forward, so what will happen? Every time it goes x forward, you can just draw this thing, a small So if you look at the pulleys here, pulleys will come here. Now notice one thing here. This part of the string will never change. This is still fixed. So whenever you move this by distance x, if you look at the pulleys here, this part here, which I'm shading in red here on the top, this will become loose. This will become loose. All these things will get loose, isn't it? So every time this thing goes x forward, we will get here x, 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 and x. Total 5x string becomes loose. So all this shaded part becomes loose. So if I push this forward by x, so the loose string is 5x. Are you getting? I'm not taking this green one because this green one ka length will remain constant. No matter how much you move it forward and backward, the length of the green ka string will never change. Is that clear? Next thing on top of it, now if you look at this block B, what it is doing, two things are happening to this block B. Because of the loose string, it is going downward by 5x. And remember, this block B also has gone x forward, isn't it? If you see from this position to this position, even B has moved x forward. So B has done two things. One, it came down the incline, and it also has gone x in the forward direction. Is the path of B clear, everyone? B is going in two directions. It is going forward because it is in contact, and it is also sliding down the incline. And this angle is theta. So if you resolve this into components, you will get velocity of B will be, this will be nothing but 5u. So u and 5u ka angle theta. So velocity of B will be u plus 5u cos theta I cap. It's also going down to 5u sin theta j cap. Have a look at this. Yeah, you can do the same thing. You can assume for 1 second, then the distance traveled will be u and 5u. The same thing, it doesn't matter. I can take x, I can take u. Is the logic clear, everyone? So it's all visualization. Like, you push it by x and see where are the strings becoming loose. All that loose string must go somewhere, and the only person who can take all the string is B. So it should slide down the incline by 5x. But at the same time, because you pushed it forward by x, it is also going forward by x. Is this idea clear? Any other doubts? Anyone not convinced with this? Anything that you're confused? Ovia?
Sir, like I did it, I took the V along the incline, so I got 5u plus u cos theta. But like
Okay.
you took.
But then what about the u sin theta then? If you're taking this u ka component, then if you take u this also, no, there'll be u sin theta also. That is also fine. Then you are choosing this as x-axis and this is y-axis, isn't it?
So there was no particular reason you took.
Nothing. I just took regularly I cap and j cap in the horizontal direction. So let's say if they ask you find the speed now, you and I will get the same answer. It only mattered like, how did we choose x and y? I chose the regular x and y. You chose x and y as incline and perpendicular to incline. So technically we're not wrong. We just chose different x-axis. But if they ask for speed, you and I will get same answer. Because normally what will happen now, they will say VA is equal to, they'll say VA I cap. Means it is understood they're taking horizontal as x-axis. Okay? That way. Arya.
Sir, I'm not convinced why the green part will remain constant. Can you please explain that?
Why it will not remain constant? Why will that change if I move the forward thing? Batao. Why will this string become loose?
Sir, I mean, it will come forward by 5x, right?
That is coming 5x because these things are coming loose now. Wo second part of the story hai.
Okay, so
This
it's
thing has
not,
to
the
become
length is
loose.
not constant, right?
Where?
For the green part?
No, the green part will remain constant. Usme extra 5x add hoga na. Matlab after
Okay,
some time
हाँ.
the picture will be like this.
I
You will
thought you
get
were saying,
5x and then you'll get the green part. The green part will
हाँ,
remain
हाँ.
same na.
I thought you were saying like the green part's length will be constant.
No, matlab, when I moved it, the green part length won't change. That's what I'm saying. Because you moved it, 5x became loose. Now it will move one after another. Clear with this? Let's see a few more like this. This is A and this is B. A is going backward. Find velocity of B at this instant. How do you handle this? Give me an I cap, J cap. Always give vectors in the velocity vector form. That is more superior. Right, Arya. Ne, Vanchika. Right, Samyak. Get the second one. I'm more interested in the second one, actually. Ne, Srihari. You're getting the directions wrong. Same idea. Push the block a little forward. So let's say I push it A till here. If you do this, the pulley will come somewhere here. You can clearly notice here, this part of the thing, right? You pushed it forward by X. And look at this string here. All this string here became loose. This part became loose. So that should go somewhere. So this block also will come down by X. That means this B is going backward with U and it is also coming down with U. Therefore, velocity of B will be minus U I cap and minus U J cap. I hope that was convincing. So whenever you push it forward, this string will become loose here. So because of that, B will come down. Because you're touching the big block, you'll also get pushed forward by U. So you'll go minus U and minus U I cap and minus U J cap. Clear with this? What is the catch with the B1 then? Minus because it is going backward, right? Right is positive, left is negative, right, Vanchika? Regular X and Y axis. What about the B part? B part answer is not same. There's a small thing. See, what happened? The moment A tries to go, this B block actually loses contact. Isn't it? If you suddenly move A, what will happen? B will lose contact. It won't be touching this thing. No? This will come like a pendulum. It will start hitting the surface from the back. So the question is at this instant. So the moment you try to move A, B will suddenly lose contact. Is that making sense? Did you ever try this thing? Think of like this. When Superman is flying, what happens to his cape? The cape is like this, isn't it? Why is the cape like that? Because if he is going this way with some speed, the cape, right, due to inertia, it doesn't come and touch the skin in the back. So the cape loses contact with the backside of it. The same way, if the Superman is wearing the cape in the front, then what will happen? It will come and stick to his face. You get in the difference between both the cases? Or did you ever do this thing? Let's say you're running behind a bus or running behind a friend with your college bag. Did you ever notice once you start running, this bag actually lifts off? It loses the contact from your back. So what you do when you're running, you actually catch the bag and then run, isn't it? So you will notice something like this. So if the moment you push this, the block B loses contact for a moment. After that, it will come swinging, hitting and all. We're not interested in all that. So you will notice here, this part will become loose. That is okay. But there is no horizontal motion. So this will just go down X. That's where the question is at this instant, because after some time you can't calculate. So B loses contact with A. There will be no horizontal motion. B will be at the same place as his, this position.
So if you accelerate both of them from rest and then make both their velocities constant.
But वो नहीं है ना. Initially, like the system is like this. You suddenly started moving A with you.
Oh, good.
That way. Now you can create all the situations, but that is not the question. So there'll be no horizontal velocity. That is the difference between this and the A part. So basically, the floor will push you. The floor will never pull you. Therefore, in this case, velocity of B will be only minus u j cap. There'll be no horizontal component. I hope everyone is clear with the difference between A and B. So just changing the orientation will change the problem. So answers won't be same. Everyone clear with this? Anyone has any doubts, not convinced, confused, please ask.
So, but
So
like,
always be careful with this.
if the question is given as it is, like you gave,
If he
and they have
says
to
like this, na,
mention
B
it.
always, if they say B always remains in contact with A, they will say that.
Okay.
See here, I need not say this. There is no doubt, na. If B is not in contact with A, B can't go into the block A.
Yes.
But here you can lose contact, na. There is no problem with that.
Sir, I mean, if they can, means this situation can be created in different ways.
Yeah,
So,
yeah, you can create it. If they tell you, na, if B is always in contact with A, then you take it, or else you don't take it.
okay.
All clear with this? Let's see one more like this. Like these questions, right? The thing is that only once you see 4 or 5 variations, you'll get the hang of it. You're basically just seeing and visualizing. There is no big concept or anything here. So let's say we got an incline. We got a pulley here. We got a block A here. We got a block C here. We got a block B here. Let's say A is going down with 2 meters per second. The wedge is going with 1 meter per second. Then what is the velocity of C? Assume C always remains in contact with the wedge. There is a possibility if I move the wedge really fast, then there is a chance that C will actually start flying in the air like this. So we don't want that to happen. How do we do this? Try. Everyone should give it a try. Hmm, 3/2 I root 3/2 J. Short, yeah, that looks right with a minus sign. Ne Srihari. Told you how to give an I cap and J caps. Minus half ne re samyak. You got the I cap thing wrong. See, when you have so many things moving, right? See, till now, all the problems you did, right? Luckily, there's only one thing moving and you just got it easily. Here, there are three things moving. So what you do, these kind of problems, move one at a time. So listen to this. Don't assume A and B are going at the same time. Let's assume first only A is going, then assume only B is going, and then see what happens. So here, first move. So assume only A moves. Then find VC, right? Then assume B moves, then find VC bar. So basically we are seeing if A moves, then what happens to C? If B moves, what happens to C? Because see, A and B are independent of each other. A ka velocity is fixed, B ka velocity is fixed. A doesn't care about B doesn't care about A, right? And then the resultant, take resultant of both. We call this in principle of superposition. Do you remember this? We did entire projectile motion like this only. If there are two events happening at the same time, if event 1 creates effect 1 and event 2 creates effect 2, then when both the events happen at the same time, you get effect 1 plus 2. Nee, Ishman. Nee, Robia. Let's see. I'll show you. I think Shreyansh, you got it. So first, let only A move. Okay. So if only A is going, forget about B here. Now you tell me, if A is going down with 2, C will go with what? C will go with 2 meter per second. Easy.
Yes, sir.
That was straightforward. So because of C, only this can will go. Next thing. Now this guy is at rest. So we are taking B to be at rest. A is moving. Now assume A is at rest because A ka job is already done. B is going with 1 meter per second. Now if B goes with 1 meter per second, you can see this part of the string will get loose. This will be the loose string. Every time this thing goes forward, that part of the string will become loose. This is how the picture will look. That means what is happening to the C? Because of this loose string, which is 1 meter in every second, the C will go down with 1 meter per second. And because it is in contact with the wedge, it will also go forward with 1 meter per second. Is that making sense? You're getting how did you split this? So here only A moves.
Sir, can you
We're
explain?
assuming.
Sir, can you explain how is it moving 1 meter per second and backwards on the slope?
if this string is getting loose, where will the string go? A though is fixed.
Yes, sir.
So where else can this string go then? It has to go to the left side only, na?
Yes, sir. Right side. Yes.
Getting
yes.
it? देखो ना, the pulley was here, it went to the forward. So ये जो भी loose string था, all that string must go somewhere. The only person who can take is C because A is rest. Like I said, A when A moves, B won't move. When B moves, A doesn't move. Is this clear? So now you take the resultant of both of them. That means C is going which way? So this C here is having, it is going up 2 meters per second because of A. It is going down 1 meter per second because of the wedge. And it is also going forward with 1 meter per second because it is in contact with the wedge. So you have a velocity 1 meter per second upward and 1 meter per second horizontally. And this angle is 60 degrees. Therefore, velocity of C will be, the horizontal component will be 1 cos 60 plus 1 minus I cap plus 1 sin 60 j cap. That will become minus 3 by 2 I cap plus root 3 by 2 j cap. Is this clear, everyone? Can you see what is happening when multiple things are moving? So you don't try to move all at the same time. Move one at a time. You will see this more clearly. Got the idea here? So because till now all the problems, right? If you see, there are only like 2 blocks moving. Look at here, A and B is moving, so it was easy to see. A and B is moving, A and B is moving. Now A, B, C, 3 are moving. Let me ask you one more like this. You guys tell me what will be the answer. Let's say this is going 3 meters per second. And let's say B is going 1 meter per second. Can you find VC? Nah, Srihari. See, when I say velocity, this is all inclusive. There are some other forces which are maintaining it. Don't worry about gravity and everything right now. If I say you're going with 3 meters per second, it is going with 3 somehow. Don't worry how it is going for now. Gravity, forces and all, we didn't even start that. We're not bothered about how these bodies acquired this velocity or acceleration, that we are not concerned. If A and B are going like this, what is the velocity of C? That's it. Get this, I'll give you a minute. Same thing, I just change the shape here and there a bit. You want to use relative motion, you can do that, but yeah, you can do that also. You can stop the wedge though. What obvious is also right. That is also a good method. You can use relative motion here. So here, if you do with respect to B, so B will think, okay, I came to rest. Now it will think A is going with. So the velocity of A with respect to B will be 4 meters per second. But remember, all the answers you get will be with respect to B only. Now, if that is going with 4, C has to go with 4. So velocity of C with respect to B is also 4 meters per second. Isn't it? So we are done. So velocity of C with respect to ground will be velocity of C with respect to B plus velocity of B in the ground frame. This angle is theta. So velocity of c with respect to will be 4 cos theta I cap, 4 sin theta j cap, and velocity of b in the ground frame is minus I cap. That's your answer. You can do that also. Here it is more easy because b and a are in the same direction. In the previous problem, it would have been a little difficult because if b goes this way, a will start swinging like a pendulum. We don't want to get into that. Then you can use relative motion also in this. Or you could have done the same way which I showed you right now. Oh, yeah.
In the previous question, I used relative motion only, but then I didn't consider the one because it was in the horizontal direction.
It won't matter because ये floor भी ये भी move करेगा ना, so it kind of works out. But you have to consider that one because see, if you stop this, then you think this pulley is coming with one, na? So this part of the string becomes loose by one, isn't it? So that one will come down, na?
Yeah.
So it becomes now the ceiling will start going with 1 meter per second. That was the reason. See, if you see this one is coming because of that only. You should include that. Clear with this? So this is another way of using relative motion. How did we get minus I cap? Why are you getting confused with this minus I cap, right? It is going backward. Why are you confused with minus I cap? Vectors, right? This is your positive x-axis, this is your negative x-axis. So if you go right side, it is I cap. If you go left side, it is minus I cap. Sure? Yeah, vector resolution. Still confused? Please ask me about that. Something you don't like I caps, I guess. Happens. Clear with this? There. So this is another type of questions, where you can see. I sent you the sheet last time. Hope everyone has checked out. So you will find few models like this also. So this is all about string constraints that we have seen. The next thing is rigid body constraints. So what are rigid body constraints? First of all, let's define what is a rigid body. Pretty straightforward definition. The distance between 2 points remains constant. So if you choose any 2 points on a rigid body, that's a definition looks pretty simple, but it's a very powerful statement. What it means is no matter what you do, you increase, apply infinite force, you do anything, you cannot stretch the body, you cannot compress the body. The body cannot be deformed. That is, they cannot be elongated or compressed. These kind of bodies are hypothetical, they don't exist. You start getting pretty weird things with this. Meaning, when you say the distance doesn't move, what does it mean even? If you have a solid body, if you look at molecules, the molecules are always in a state of vibration. So if there are two molecules and they're vibrating, that means the distance will change. So in a rigid body, the molecules are not supposed to vibrate. That means the body is in 0 Kelvin temperature. A rigid body will be pretty cold. A rigid body does pretty weird things. A rigid body, if you push this molecule, because the distance has to be constant, at the same time, all the molecules will move the same distance. Means you can transmit information faster than speed of light. So it doesn't work. So these things don't exist in nature. But like again, we will assume most of the time, bodies are rigid body. So these are hypothetical, they don't exist. But most of the things we study are for rigid bodies. Yeah, but day-to-day purposes, we can almost assume it's kind of valid. Clear? It's again, we are going to talk about rigid body in rotational mechanics. So there we are going to have a lot of uses for this. So consider a rod. So let's see, how do we use this? How does this create constraints? So if nothing is mentioned, assume it is rigid body until unless it's mentioned. Consider a rod with ends A and B. With velocities VA bar and VB bar. So let's say we have a rod here. This is A. This is going with VA bar. It's a thin rod. This is going with VB, and let's say this angle is theta 2. So you might think like, how can a rod have velocities like this? These kind of velocities are possible when you have a rod which is translating and rotating. If you have a rod which is translating and rotating, you can get these kind of velocities. Did you ever play a pen game? When you play the pen game, if you hit the pen here in this corner, how does it move? Isn't this thing will rotate and go forward? So you have a rod which is translating and rotating. So when you have these kind of velocities, when the rod is rotating and translating, it is possible to get these kind of velocities. So you can split this into two components. So if you resolve this, the vertical component will be VA cos theta A. The horizontal component will be VA sin theta A. This vertical component is VB cos theta B. This component will be VB sin theta A. We are interested in the components along the rod. Now see, if VA cos theta A is greater than VB cos theta B, means if the person in front of you is going faster than you, what will happen? The distance between you and him will increase. So the rod should elongate. If VA ka component becomes greater than VB ka component, rod will start stretching. But you said it is a rigid rod, so rod cannot stretch. If you say VA cos theta A is less than VB cos theta B, that means the person behind you is going faster than you, then the rod should compress. Because if the person behind you is coming faster, he'll get close to you. But we said it is a rigid body, it cannot compress or elongate, then there's only one possibility. They should be equal. There, this is your rigid body constraint basically. So on rigid body, if you take 2 points and if you draw the line joining them, the velocity along the line joining must be same. If it is not same, the rod will either compress or elongate, which is not acceptable. Is the idea clear, everyone? Unlike strings and all, the idea is pretty straightforward here. So let me put this in a more general form. So component of velocities along the line joining 2 points must be same. That means if you take some random amoeba shape, and if you choose 2 points here, A, and if you choose a point B here, and if you say this is going with VA, and this angle is theta A, and if you say this thing is going with VB, and this angle is theta B, so it need not be a rod every time, it can be any shape. So velocity along the line joining them, so this component will be VB cos theta B. This component will be VA cos theta. These two must be same, or else the distance between them will change. Clear with this? So you can extend this further. If two surfaces are in contact, then velocity along the common normal must be same. Same logic. If the velocity on the common normal is not same, that means either they'll separate or they will push into each other. What is a common normal? Look at the word common normal. What is normal? Perpendicular to the surface. So if you take an incline and a ball, the common normal will be this. The line which is perpendicular to both the surface of the sphere and this thing. Suppose if you have a surface and a block. So for both of them, the common normal is this, perpendicular to both of them. Suppose if you have a sphere, big one and a small one, the common normal will be a line passing through the center. So if two balls are colliding or doing something, the velocity along the common normal must be same. Again, think about it. If it is not same, what will happen? Suppose if these two are there, in this direction, if the velocity is not same, there are only two possibilities, meaning either this is going faster than this. So if V1 is greater than V2, this ball will fly off. If V2 is greater than V1, this ball will go into the wedge. Both are not acceptable. That means they must be equal.
So technically, the wedge will go into the ball, right?
Yeah, whatever it is. So same thing. Clear with this? So this is the whole idea there. If two rigid surfaces are touching each other, velocity along the normal must be same. Any doubts on this? Let's see a question based on this. So we have a wall here, right angle triangle. We got a rigid rod. Length L. So we have a point A, we have a point B, and C is the center. Now what happened? Someone started dragging this point A with a constant speed U. Right? And assume B is always in contact with the wall. Find velocity of B and acceleration of B. First question, find velocity of B and velocity of C. C is the center. Second thing, find acceleration of B. Let's get these two. Shreyans, VC is wrong. I'm more interested in VC and acceleration of B. Let's get those two. Yeah, I think VB, most of you got it. So let me help you with BB. Same story. Just now, what did I tell you? If you take 2 points on the rod, velocity along the rod must be same. Right? Now here, luckily, since B is always in contact with the rod, I'm pretty sure B is always going down. Do you guys agree with that statement? You're getting it? We can be sure that B is always going down because it's in contact with the wall. If B has a horizontal component, then it will lose contact with the wall. Unfortunately, you can't say that about C. Problem with that C is that C ka velocity, I don't know. It is going in some random direction. But B, I'm sure. So this is how they're going, VB and VA. Then what's the next step? Draw a line joining A and B. So if this is theta, this is theta. This will be 90 minus theta. Then the components along the line joining must be same. So this component will be VA cos theta. This component will be VB cos 90 minus theta. Since length of the rod cannot change, these two velocities must be equal. So VB sin theta is equal to VA cos theta. Therefore, VB is equal to U cot theta. Is this clear? Velocity along the rod must be same. B moves vertically down since it is in contact with the wall. How do you find VC and how do you find acceleration of B? Think I'll give a minute more. Till here, it is a standard question. This will be like a straightforward CET or a mains level thing. Multiple times this thing is asked. But if I ask you the speed of the center or the acceleration, that's something else. Acceleration of B. No, Arya, that is wrong. Try. Everyone should give it a try. I'll give a minute. VA cosecant theta. Okay, let's see. Let's find the acceleration of B first. So what do you do with the acceleration? Differentiate. So VB is U cot theta. Remember, theta is also variable. So acceleration of B will be dVB by dt. I told you this, you can't use these formulas for accelerations if theta is changing. So this will be U d by dt of cot theta plus cot theta du by dt. Luckily, u is constant, so this term will be 0. What is differential of cot theta? Cosecant square theta. Cosecant square theta, then you end up with d theta by dt. You can use the division rule, cos theta by sin theta, and check it out. This is your acceleration of b. Now the problem, how do you get d theta by dt? This is kind of looking like that problem we did, the strings mein, when theta was changing. This angle was theta. Let the distance be x. This was length L. Cos theta is equal to x by L. Differentiate both sides with respect to time. You always need to get that in terms of x. Cos ka differential will become minus sin theta and d theta by dt. This will be 1 by L dx by dt. The reason x is changing is because of velocity of A. So minus sin theta and d theta by dt is nothing but velocity of A by L, which is u by L. So from here we get d theta by dt is minus u by L sin theta. Later on, I'll show you in circular motion. You can get these things even faster, but for now, let's bear with this. You're done. So once you get this, take this and dump it here. This will be minus u, cosecant square theta is sine square theta, and d theta by dt is minus u by L sin theta. U square by L sin cube theta. This is your acceleration of p. That's what makes these questions. This will be an advanced paragraph, more than one choice questions. Check it out. This is how you find acceleration. And last time we have seen two problems like this, isn't it? The theme is the same. We still have to find velocity of VC. How do we do that? Any doubts on this page, please ask me. I'll show you Sika velocity. See. So when you look at this rod, you said C is the midpoint. That solves all the problems actually. So for this point A, let the coordinates be x, 0. Let this point B, the coordinates be 0, y. Since C is the midpoint, the coordinates must be x by 2, y by 2. Therefore, the position vector of C must be x by 2 y cap plus y by 2 j cap. That means velocity of C will be dr by dt. That comes out to be half dx by dt I cap plus half dy by dt j cap. So this is going BA and this is going VB. So this distance was x and this distance was y. So dx by dt is nothing but velocity of A, which is u. dy by dt is minus VB because y is decreasing. This is minus u cot theta. You're done. Substitute here. Therefore, velocity of C will be dx by dt is there. So u by 2 y cap minus u by 2 cot theta j cap. C ka velocity is not constant. It is going in some weird way. So it will have half of the velocity of A and half of the velocity of B. That's it. That is the idea there. Because it's a midpoint. Is that clear, everyone? That is how you can do for C. Since I know A and B, I'll find the midpoint coordinates and finish it off. Now the problem, if you try to use that formula, right, velocity along the rod is same, that will help you. But the problem is you'll only get this component VC. You won't get this perpendicular component of VC. I don't know how to find this directly. So we'll go with the coordinates. Check it out. This is how you can find velocity of C. Remember, this is pretty good question. Yeah.
Sir, can we find the second component using d theta by dt?
What?
So can we find the, like you said that we don't know how to find a perpendicular component.
Yeah,
So can we find the component by using some equations which use d theta by dt?
we didn't do circular motion yet. I
I
already
mean,
told
sir,
this
can we do
multiple
it like,
times. So you do it, na? Do it and then show me whether you're getting it or not.
sir, I'm not sure how should I apply that.
सोचो ना then. Idea तो तेरा है. You
Okay,
can
sir.
do it. करके देखो. You can do it. It is possible. Now you try. Clear with this? If you stand on A, you will think C is going in a circle. Find velocity of C with respect to A and then add velocity of A with respect to ground. Then आएगा. Try that. Anyways, we will see that later on. All clear with this problem? Similar one. You guys tell me what is the answer for this. I'll keep it more simpler one. What if your incline is like this? Let's say this is A, VA is going with U. This is B. Let's say this is 120 degrees and this is 30 degrees. Find VB. You can even find C. I'll leave you to that as a homework. I'll teach you this in rotational mechanics again. There's a much faster way to do these things in rotation. But for now, let's handle this. Just find VB now. VC, you can try it as a homework. Yeah, this was easy. Right, Shreyans. Right, Obvio. क्या था? That angle is also 30 degrees. If that is 120, 30, the total angle has to be 180. So this is also 30. So we know B goes this way. It's because it's in contact. So you should take components along this line. So this is also 30 degrees. So this component will be VA cos 30. This component also will be VB cos 30. So this was straightforward. We get VA is equal to VB. Find C. That is an actual question. I'll leave that to you as a homework. Story is the same. You'll somehow figure out the coordinates. You can take this point as origin, get the coordinates, and try to do something. Clear with this? Go take a break. Come back by 9:35. We'll continue from here. Any doubts so far? Chalo, come back in 5 minutes. There, we got a wall on the right side. We got a ball here. We have a wedge here. This is theta. Someone started pulling this wedge with you. B always remains in contact with the wall here. Same thing if I do it like this. This time there are two inclines. Let's say this time C is going with 2u. K is going with u. Find VB, get both of them. You know where you have seen this picture before? Remember this picture? Find N1 and N2. We did this in equilibrium, these kind of questions. So we'll see later on, these things will pop up. For now, it's only constraints. We are not interested in the forces and all. If I pull that A with U backward, left side, you know what will happen? This wedge will come here and the ball will fall down. So the ball keeps coming down. Give me in terms of I cap, J cap, God. Here everything is in theta. Where are you getting that numbers also? Arya. Keep your cam on. Try. Take a minute. Let's get the first one. I'll show you the first one in a minute. U plus U minus U. And let's see the first part. Again, whenever two surfaces are touching each other, what will happen? The velocities along the common normal must be same. What is your common normal? This is your common normal, isn't it? The line joining the center and this thing perpendicular. Great. Then how are these velocities going? Look at this. This point is the velocity of A. Here, this is velocity of B. So B is coming down and A is going to the left. If this is angle theta, this is 90 degrees. This is 90 minus theta. This angle will be 90 minus theta, and this angle will be theta. Are the angles clear? So along that red line, now if you look at the velocities, this is VB and this is theta. This is VA and this is 90 minus theta. So velocities along the normal must be same. So this component will be VB cos theta. And this component must be VA cos 90 minus theta. Since both the ball and the wedge are always touching each other, these two velocities must be same. Because if these two velocities are not same, then either the ball will lose contact with the wedge or the ball will go into the wedge like this. Both are not acceptable. So we have VA cos 90 minus theta is VA sin theta is equal to VB cos theta. So VA is U and this will become tan theta. There. So whenever you pull the wedge with U to the left, the ball will come down with U tan theta. Is that clear, everyone? So the same question, right? You'll also see it in the books like this. You have a wedge. We have a circular thing like this. And you have a rod inside. This is there in the SN which I gave you. And this is another standard question basically. So we got a rod here which can go only up and down. If you look at actually both the questions, they're exactly the same. So I'll just change the shape bit.
Sir, like, can you explain this question once again?
Which question you're talking about?
Sir, this one only which you solved, because I was getting a different answer.
So that, what does that has to do with the explanation of the question? What did you do?
No, I tried doing the same thing, like common along the common normal, the velocity would be the same.
So there I did the same thing. Which part you didn't understand? The angles. See now, look at this thing. Did you mess up the angles? Did you mess up the component? Which part you didn't understand?
Sir, like, could you explain you taking the angles once again, like, because I think I messed up there.
So if this is theta, this is 90, this is 90 minus theta, alternate angles 90 minus theta, this is theta. Because this will be another right angle triangle.
I took that VA also theta only, that is why I was getting wrong.
So,
Okay, sir.
So say na, you're messing up the angles.
I see.
You are saying like, what sir, explain the whole question.
Sorry.
Then, what will I assume? I'll assume you didn't understand the question ka diagram only.
Sorry, sir.
No. Sorry, nahi. You guys ask properly, right? Because in the class I'll explain. Tomorrow when you go to engineering, no one will. If you ask like this to the professor, he will just look at you weirdly. He will just throw your thesis paper outside. You guys are very bad at asking questions. Learn to ask properly. Like you should have said, sir, I'm not getting the angles right. That would have been good. If you say, sir, explain the question, I'm assuming like, why didn't you understand this question? I was confused. Anyway, so look at this thing. The same question that I could have asked you in another way. Instead of a spear, I'll put a wedge like this. So if this is going with U and this is going down with VB, you get the same answer. Clear with this? So both the questions are of same thing. Instead of a spear, we have a rod coming down. So this was there in the sheet which I gave you. So this is a standard model. I just made it into a spear. What about the second one? How will you do this? Try, I'll give you a minute. A is also moving, C is also moving. The ball now, is there any guarantee B will come down? B won't come down. B is moving in some weird way. How will you do this? Try, you got a minute or two. I'll show you this in two ways. I'll show you one faster way and one general method. General method you need to know because every time you won't be so lucky to get it an easy way. Any ideas? Okay, Arya did get something. Now see, there is a way to do this thing. Both the problems will actually, they can become same if you do something. Can you stop C? If I stop C, doesn't this behave like a wall now? Then the problem A and B will become same, isn't it? So that is one thing. When you see multiple things moving, always ask yourself, is there any possibility I can stop one of them? Sometimes you can, sometimes you won't be able to do. Sometimes even if you stop, it really won't help you much. But in this case, you can stop. This is theta, this is theta. This guy is going with 2u and this guy is going with u. So if I stop C, that means if I try to do the problem with respect to C, now this C will behave like a wall. This comes to rest. So a person standing here, he will think, okay, I am at rest. This has literally become the wall. And this person will think this A is going backward. So this is velocity of A as seen by C is 3u backward. Now this has become like question 1, isn't it? If A is going back with u, then this will go down with what? 3u tan theta. We proved this just now. This has become like part A. That means C will think velocity of B as seen by C, C will think it is going down with 3u tan theta j cap. This is what C will think. So if you want in the ground frame, velocity of B as seen from the ground is velocity of B as seen from C plus velocity of C with respect to the ground. Is this equation clear, everyone? This is that moon and sun ka example, remember? If you want to study moon from sun ka frame, we'll see sun to earth and then we'll see earth to moon. So B to C is 3u tan theta j cap. And C is going to the right side with 2u. So 2u I cap. That's your answer. Check. So there, if you stop C, life becomes pretty easy to do. It just becomes like part 1. The C will behave like a wall. Okay with this. But like I said, here you're lucky. The numbers and everything are matching out. It works out. Every time you won't be so lucky to get this. So I'll show you a one model like that also. But how to do this generally? So listen to this thing. This is how you do this general solution. A little lengthy, but yeah. Since you don't know how B is going, always assume velocity of B to be in 2 directions. Let the velocity of B VB bar be Vx I cap, Vy j cap. So if I can find Vx and Vy, my job is done. So every velocity can be resolved in 2 perpendicular directions. So listen to this. Next problem is based on this only. So this is C, this is A. So this guy is going with 2u. So what are the common normals here? So this is Vx, this is Vy. So I'll assume 2 directions, Vx and Vy. So there are 2 common normals here. So this is the normal between B and C. This is a common normal between A and C. Now from the rigid body constant, we should know velocities along the normal must be same. So for B and C, if you look at the velocities along the normal, this is going with Vx, this is going with 2u. There, so Vx is equal to 2u. There, we got it, Vx pretty fast. So velocity along the normals must be same, or else B and C will lose contact. The headache is A and B actually. So if you look at A and B components, this is your normal. This is angle theta. Again, be careful with your angles here. This is going with U. This is going with Vy. So if you extend this line here, this is 90 degrees. This angle will be 90 minus theta. This angle will be 90 minus theta, and this angle will be theta. Shaurya, clear with those angles? Everyone clear with these angles, right?
Sir, actually, I had one more question.
What is the doubt?
Sir, like for example, here we like know that we can easily put C as a wall and then solve this question.
Yeah.
Like, but in those cases which we can't do, but we'll still try to do. So like, could you tell when we should apply this method and when we should not?
If you wait till I teach you, you will understand. If you are
Okay.
unnecessarily being impatient, so have some patience. Where am I running away? So if you take components in the direction of the normal, so this component and this component must be same. So Vy cos theta must be equal to u cos 90 minus theta. But unfortunately, Vy is not the only component. There is Vx also. So we should take Vx ka component also. That is the thing. This method is messy. But there are cases I'll show you where you won't be able to do without, the relative motion won't be so easy to handle. So this is Vx and this will be 90 minus theta. So now if you look at the components here, this component and this component. So this will be Vy cos theta minus Vx cos 90 minus theta. So there are two components for Vb. That must be equal to u cos 90 minus theta. Are you getting how am I taking the components? You should take Vx ka component, Vy ka component must be equal to u ka component. So all components along that line must be same. So this will be Vy cos theta. Vx we already know 2u sine theta. And this is u sine theta. If you solve this, you'll get Vy is equal to 3u tan theta. Didn't we get the same answer? So Vx is 2u on the right and 3u tan theta to the down, which we got it pretty fast with relative motion. But in this method, you have to put little effort. Clear with this? This is how you do an alternate method if you take Vx and Vy. Any doubts on this method? So velocity along the normal is same. That is the only concept we are using. So let's see a question where the relative motion thing you won't be able to handle it that easily. Any doubts on this page? Next one. Now you guys try this. And then if you got this rigid body constants, you're clear. So let's say we got two wedges like this. You got a wedge like this in the middle. This is A, this is B, this is C. This is 37 degrees, this is 45 degrees. This is going VC with 10 meter per second. This is going VA is 5 meter per second. Find VB. So VB is that trapezium kind of shape. Now here the problem with the relative velocity, if I try to stop C, the B is going down also, it is going at an angle also. You can't say it like the previous one. This becomes a little complex that way. Can be done with relative also. But that's what I'm saying. In the exam, unnecessarily you'll keep thinking like, should I use relative? Should I use this? And you will waste your time in thinking only what to do. Better stick to one general method which you can handle in every model. Let's see. How do we do this? How do we start? Vx and Vy. Let's see. This is a little lengthy. So there are two normals here. So this is one normal. So you want velocities in this direction to be same. This is another normal. Velocities in this direction also must be same. So let's start with an assumption. Let B go with Vx and Vy. So B ka velocity, let it be, it's going horizontally with Vx and vertically with Vy. So take the components here. So this is Vx. This is Vy. Luckily it is 45 degrees. So this is also 45. This is also 45. And this is Vc. This is also 45. So components along that normal will be Vx cos 45. Vy cos 45 will be Vc cos 45. So we get Vx plus Vy is equal to 10. That's your equation 1. Then for this thing, this is your Vx. This is your Vy. Again, be careful with the angles here. This angle is 90 degrees. If that is 37, this angle is 53 degrees. If this is 53 degrees, this is 37 degrees, and this is 53 degrees. Are the angles clear, everyone? Just geometry there. And your B is going this way with 5. A is going with 5. If that is 53, this angle is also 53. Again, velocities along the normal must be same. So VA cos 53 must be equal to Vy ka component is downward, so Vy cos 37. Vx ka component is upward, so it will subtract Vx cos 53. Please ask me if you're confused with the equations. Check out the equations. Please ask me. So you have to take the components of Vx and Vy along this line and Va along this green line. Similarly, for Vc, you have to take in this green line and Vx and Vy in this line. So if there are two normals, velocity along the normals must be same. Then right, okay, you got it. If you got the equations, your job's done. Anyone confused with these equations, please ask. Anyone didn't get the equation, the sign, the direction, anything you're not convinced? Right, Samyak. Clear, Shaurya? Shaunak? Arya? Clear with the equations? Aditi? Advai? Devanshi? Yashvi? Trishi? Clear? So what's cos 53? 4 by 5, 3 by 5. Cos 37, 4 by 5. This is also 3. So this is a 15. is 4Vy minus 3Vx. There we have two equations, two unknowns. So you can simplify this. So take Vx here and substitute. So we'll get 4Vy minus 3Vx will be 10 minus Vy is equal to 15. That will become 30, 45. So Vy will be 45 by 7. If Vy is 45 by 7, then Vx will be 70 minus 45, 25 by 7. That's your answer. Check out the steps. So 25 by 7 I cap and 45 by 7 minus j cap. So if you are confused, how is the body is going? For example, see in the previous problem, you are clear in the first part. In the first part, it was pretty clear B is going down. So there was no doubt and your life was easy. If I give you something like this, you have no idea how that B is going. The only way to handle these kind of problems is assume Vx and Vy, draw the normals, get the components. There, this is how you handle rigid body constraints. Clear with this? There, these are the two types of constraints, string constraints. In string constraints, we saw three types. The first thing was the length of the string constant. We are not going to use that. We are going to use the power method, and we're going to use the third method where we started moving the blocks and visualizing things, and the rigid body constraint. This whole thing is constraint motion. Like I said, in the laws of motion, this is the first part of the chapter. The second part is free body diagrams and everything. That's a little more easy, but again, quite important. So if you know how to handle constraints and if you know how to handle free body diagrams, the rest of the chapter, you'll be able to get it. Most of 80% of the chapter is over. Yeah, but solving, we will see different models though. There, that's a bit about constraints. So next thing, laws of motion. So we got a bit of a theory. So Newton's first law. So what is Newton's first law? So it says a body continues to be in a state of rest or uniform motion until and unless a force is acted upon it. So here, if you see, right, first law talks about two things, a state of rest and something called force. So these are the two words it talks about. So like I said, we have discussed this thing a bit in kinematics. How do you know something is at rest? It depends on your frame of reference, isn't it? So it gives us the concept of inertial frame. So the first law tells us something about inertial frame. And it also talks about something called force, which is responsible for moving things. So until unless you apply force, things are not going to move. Clear? Now, there are four types of forces that we have. So all forces in the universe, right, can be classified into four types. The first thing, gravitational force.
It should be an external force, right?
Right. So this comes because of due to the interaction between the masses. What is external force record? What are you talking about?
I mean, the force can't be internal, no? Which changes the state of rest or the uniform.
There is nothing internal, external. Let's not go ahead, Aryan. So focus what you're doing. right? I know you know things, but don't go ahead, don't jump ahead with a lot of things. There's nothing called internal and external. It all depends on what is the system. So don't get confused with this stuff. You want to move a body. So here we are talking about a single body. What is external? What is internal? You're talking about here. So do keep your cam on. So a gravitational force is due to the interaction between the masses, and this thing has an infinite range. Meaning it can interact with bodies up to very long distances, and it's a very weak force. So if you talk in terms of range and strength, see, when I teach you, I have to teach you under the assumption you don't know anything after this. I know in your classes you must be going ahead, but don't try to bring all that stuff and mix up things. Unnecessarily, you'll confuse yourself. We will go one at a time. So this is a gravitational force. What is the second type of force? Electromagnetic force. Right? In the class, we do everything. We do mains level, we do advanced level. We are going gradual level and taking up. So have some patience. Have some little trust that, I'm going to cover everything. So you're still confused, you can stay back after the class and let's discuss. So what is electromagnetic force? This is due to the interaction between charges. That was basic stuff. And what about the range of this thing? This range is generally up to meters. This thing is kind of strong compared to the gravitational force. Third kind of force is a nuclear force. So most of our 11th and 12th portion will stick with only the A and B force, the gravitational and the electrostatic forces. So what is this nuclear force? This is due to the interaction between the nucleons, that is the protons and neutrons. This thing is very small distance, 10 power minus 15 meters, very Fermi. That's a 1 Fermi. And these forces are very strong. These things we don't deal with in day-to-day life. There's a fourth type of force in the universe called weak forces. So this is something people are still studying, the dark energy, dark matter, all this stuff. So we don't know why this comes. We don't know the range. We don't know the strength. So the last thing, we have no idea what it is. Still being under studying. So we are mostly interested in A and B, the gravitational forces and the electromagnetic forces. So in the universe, right, no matter which force you take, it has to be among these four. It will be classified among these four forces. So you call a normal reaction, friction, all these things will fall under one of this category. Clear with this? There, just a bit of a theory there. No. But we are more interested on, the forces which we deal in mechanics. So in mechanics, we deal with normal reaction. We already heard these words a bit. Tension. Spring forces. And friction. So in laws of motion chapter, we will deal with normal reaction, tension, and spring forces. Friction is like a weird one, so we have a separate chapter for it. It's a rogue actually. It behaves very weirdly and differently than the other forces, so it deserves a own chapter for itself. So in this chapter, we'll primarily deal with normal reaction, tension, and spring, and friction we'll see in the next chapter. So first, let's see what is normal reaction. The symbol is N. So the normal reaction, it comes when two surfaces are in contact. Right, with each other, there is a repulsion between the molecules. The nucleus of the molecules repel each other because see, the nucleuses are concentrated positive charges. Generating a force along the common normal. So what kind of force is normal reaction? This is electromagnetic. So right now you're sitting on a table, the chair is pushing you up. You're catching your pen, the pen, right? There's some kind of force between you. All these forces are electromagnetic forces. So if you take two surfaces like this is how it looks. So the molecules on this surface are repelling this. This will repel like this. This will repel like this. You can see by symmetry, the force will be along the common normal. This is repelling this molecule. This molecule repels this. This thing is repelling there. So the molecules are repelling each other. So they generate a force along the common normal. Since the force is along the normal, we call it normal reaction. So if you have a wedge and a block, the normal force will be in this direction. So they push each other along this red line. They push along this line. So they push along the common normal. So when two balls collide, the force will be along this red line. So common normal. There, that's your first one. So normal reaction will always act perpendicular to the surface. That's why we call it a normal reaction. Any doubts on this thing? All clear with this page? Any doubts? Anyone not clear with this? There, that is your first force, normal reaction. So whenever they say normal reaction, it is simply you have to draw it along the normal, and this comes because of nuclear repulsion, the repulsion between the molecules. Next thing, tension force. First of all, when you say tension, we actually use the word wrongly. Tension is not a force. Tension is the state of the material. When you say the body is tensed, you're talking about the state of the material. Think of like this. You're angry. Angry is being, it is a state. Because you're angry, you start shouting and you start fighting with everyone. So that is an action. So same way, when the body is under tension, it generates internal restoring forces. So the forces generated because of the body being in tension are called tension forces. But for some reason, right, we are too lazy to call it full word. We simply, instead of calling it tension force, we call it tension. So when a body is under tension, it generates internal restoring forces. Which try to bring the body back to the natural length. Look at this word, internal restoring forces. So the word itself explains. So when you have a body, these forces will occur inside the body. These are restoring forces. Matlab, restoring means what? They are trying to bring you back to the natural state. So these are the forces which are generated, which will try to bring you back to the natural state. That is the meaning of that whole word. So this is what we call as tension forces. So when you take a rubber band and you try to stretch it, inside the rubber band, you will have some kind of forces will generate, which will try to bring you back to the normal state. That's the reason when you leave the rubber band, it comes back to the normal length. So instead of calling it tension forces every time, we will call this thing as tension. Technically, tension is not force. Tension is a state of material, but yeah. So what kind of force is this? Tension is again electromagnetic force. So tension comes because of the deformation in the bond structure. So when you're taking the molecules and you're trying to stretch or compress, the molecules are getting deformed. The molecules are pushing each other to generate this force. So tension is also due to electromagnetic force. So at a molecular level, tension, normal reaction, friction, spring force, all these things are electromagnetic forces. We did study about tension a bit in the constraints. So what is the difference between a string and a rod? So let's see that difference there. So if you take a rod can pull and push. So a rod ka structure is in such a way, right? It will try to oppose you in both the ways. All basics, but you should be clear about each and everything. So let's say you pull the rod. If you pull the rod pulls you back. If you push the rod will push you back. The rod is simple. It pulls back. If you push the rod, it pushes back. That means you can have a scenario like this. If you take a rod and put a block like this, M, the rod is good. The rod will pull you up. You can also take the block M and put the rod down. This is also fine. The rod pushes back. So here, rod pulls up. Here, the rod pushes up. Because here Mg is pulling down, so it will pull the block up. Here Mg is trying to push down, so the rod will push up. But with the string, we have a problem. We saw this in strings. Strings can only pull, they can't push. So if you have a string and you pull the string, so there's no difference between a string and a rod when you pull. The problem comes when you try to push. The moment you try to push, the string becomes loose. There's no tension. That's it. So just remember this difference. Rods can pull and push, strings can't do this. So if you take a block and if you put a M, so the string pulls you up. But same thing, if I try to do the reverse, the moment you do this, the block will just collapse. The string cannot push back. Clear with this? There. Now, regarding the spring force, we will see that at the end of the chapter. That is a little different topic. So basically, we will currently deal with only normal reaction and tensions for some time. Then we will talk about spring, and the next chapter we'll talk about friction. Any doubts on this page? All clear with this? Oh yeah, got something?
Just like someone asked that if string is a rigid body or not, but we cannot comment about it, right?
String is a rigid body or not? See, the problem with that rigid body, right? Like I said, the distance between the 2 points should not change. That is the definition of a rigid body. Simple.
But this, when you, like, the string gets lagged, it does not get.
Think of like this: when you pull, it behaves like a rigid body. When you push, it doesn't behave like a rigid body. So depending on whether you pull or push, it can behave either way. Clear? So we can say like that. When you pull, it is as good as a rod, like a rigid body. But the moment you try to push, it goes off. Next thing. So before going into the second law, a little bit of this thing. What is momentum? Anyone has an idea what is momentum? P bar is M into V. Great, that is a definition, but anyone has an idea what does it mean? What is momentum? What does it mean? Well, this is something, right? I keep telling you, like, whenever you learn something in science or anything, remember this. There are always two definitions. There is one standard textbook definition for you to just write in the exam. That is great. But you should always have a definition for you to understand. Getting it? Now, that definition need not be a statement. It could be an example also, but getting it, you should always have something which you can understand. Okay, momentum means this. So let me give you an example. Let me ask you something. I did ask you this before also, I think in foundation maybe. But let me ask you again. Let's say if something is going with a speed of 1 centimeter per second, can you stop it? If something has a mass of 1 gram, can you stop it? So if your local train is coming with a speed of 1 centimeter per second, you'll go and stand in front of it. If a bullet is coming with a speed of 1 kilometer per second, you'll go and catch it. What happened? 10 seconds before, you're pretty confident you can stop anything with 1 centimeter per second. The moment I said local train, you got scared. When I said 1 gram, you are like pretty sure you can stop it. When I said 1 kilometer per second bullet, you got scared. So the thing is, you're not actually scared of the speed, you got scared of the mass of the train. You didn't get scared of the mass of the bullet, you got scared of the speed of the bullet. So when someone asks you this question, can you stop it? Instead of asking for mass or velocity, you should ask what is the momentum. So from that logic, right, you can define like this: higher the momentum, more difficult to stop the body. Yeah, not exactly a textbook definition, but something which will make you visualize, okay, that's what it kind of means. So if a body has more momentum, it is more difficult to stop it from moving. And anyway, if a train is going at 1 centimeter per second, if you stand in front of it, that's a horrible death. Your body will get crushed centimeter by centimeter, and you can actually feel it while dying. But if a train hits you at full speed, right, by the time your bones and everything break, your brain gets smashed, so you don't even feel any pain. So don't stand in front of a train, first of all, in any way. Anyway, so that is one. You can make a horror movie out of it. So kinetic energy is half mv square. This is one good thing. We will keep using this. We saw this thing in units and dimensions and errors, if you remember. You can multiply and divide by mass. This becomes p square by 2m. So you can also write momentum is equal to root over 2 times mass into kinetic energy. Keep this in mind. Third, Momentum also depends on the frame of reference. So depending on who is seeing the body, they will say different momentums. For example, if a block is going with m and speed u, if you have two people, let's say A is there on the ground at rest, and B is there who is going with speed v. If you ask A, what is the momentum? A will say momentum is m into u. If you ask B, what is the momentum? He will say it is m into u minus v. So depending on who is seeing the body, the momentum can change. Clear with this? There, that's a bit about momentum. So next class when we catch up, we'll continue from here. So this will be the basis for the Newton's second law. So we will define Newton's second law as force is rate of change of momentum, proportional to rate of change of momentum. So for that, we need to know what is momentum. So there. So next class when we catch up, we'll continue from here. We're going to do a little, we're going to talk about second law and third law. Those are more important. And then we are going to do something called free body diagrams and equilibrium problems. We have done some equilibrium problems in vectors, but we are going to do again repeat of some other different models. I think once we're done with that, and then I think we are ready. We all the basics will be done. Then we can go ahead with more complex problems. Okay, but we have, please make sure to go through all these constraint problems. We have did around 19 problems. So do revise them once and go through the sheet that I sent you also, because I don't think you will find constraint problems, in booklets. Like they'll be all scattered, or you might only find one or two models. So try to do that sheet. I'll send you one more sheet tomorrow, so you get more models to solve. Okay, with that we'll wrap up for the day, right? And do remember there's a test online till Thursday night, so make sure to give it.